All right. Hello, everyone. It's been a while since I last did a stream, but I thought to do a stream and complete the attention is all you need problem set on TensorTonic, and maybe do a cheeky run through the annotated transformer guide. So yeah, we'll see how that looks like. Let me try to share my screen so we have the problem at hand. All right. All right. Hope you can see the screen properly. I'll just make it a little bit bigger because I think in some of the other videos, the screen looked quite small. But yeah, hopefully this looks much clearer. Let me just turn it down. How does it look like? Okay, sure. Actually, I like it more light mode. All right. So yeah, I guess just before that, let's take stock. Let me take a stock of where I'm at, and like what we have covered are the attention is all you need paper, right? Like, so we covered tokenization, which is a method to convert text to integers, and then the embedding layer, which is a mapping between the token IDs and respectively the tokens to vectors in some embedding dimension or like embedding space. And then like the embedding dimension or like the number of dimensions used for the embedding space becomes like a hyperparameter or like a parameter that categorizes the model that you built by, and that's a number like dimension of embedding. And then you inject the input, which at this point is the position, which at this point is the embedding matrix with some positional sense of where each token, so that each token knows where it is, so that like when the learning begins, the model can learn that different tokens have different positional dependencies. And it seems that there's an interesting paper or like a blog post by Jane Street where the headline is like, the title is using group theory to explore the space of positional encodings for attention. And I'm thinking of like maybe just going through this blog post when I understand the theory of positional encoding a bit better, because I thought it was pretty interesting the first time I went through it, and much more, much more interesting and conceptually difficult than I anticipated, because I thought it was just like a light, like a scalar injection, but it doesn't seem to be that way. And then you introduce the main paper, right? Like the attention is all you need paper. It introduces the concept of like as the scale dot product attention, which attention has like other precedents, which, for example, in this blog post, by Lilian Wang covers like very deeply of all the different ways attention, or like the scores between data points or like tokens can be calculated. And then there's the multi-head attention, where instead of having like a big block of attention, you split it into like different small attention heads, which can learn different things and then like compile them together. And then the feed-forward network is a very kind of simple multi-layer perceptron, which has like its own weight matrix, and then like a bias, and then like a softmax, and then like another weight matrix that gives you the output. And the layer normalization, if I remember correctly, let me see. Kind of forget. Yeah, it before the output becomes like the output, it goes through this process, which normalizes the features, or like normalizes the output data, right? Yeah, and now we are at coding, or like creating and compiling all of them into the single encoder block. So the attention is all you need paper has, I guess let me see if they have it. Yeah, they have two blocks that they are trying to like explain, which is the encoding block, the encoder block, and then the decoder block. And most of the generative models are like just the decoder block, right? Like, so they have some input. They have some like preliminary input, and they just keep like regressively generating using the decoder model. The encoder model, a pure encoder model could be like an embedding model, and a model that has both encoder and decoder could be like a seek-to-seek model, kind of like translator, like a translation model, or like an image generation, or like a text-to-image generation model, and things like that. All right, let's see. Let's go back and look at the problem. Let me just drink some water. All right. Yes, the problem is implement a concrete transformer encoder block from the attention is all you need paper. The encoder block combines multi-head self-attention and position-wide feed-forward network, each wrapped with a residual connection and layer normalization, such that x prime equals to layer norm, and x prime in this case becomes like the final output vector, equals to layer norm of x plus multi-head attention of x, x, and x. Okay. And output is layer norm of, I see. So x prime is not the final output. I just completely lied. So output equals to layer norm x plus feed forward of x prime. Okay, so this one adds the residual before the vector goes inside, right? You need to implement 4 functions that work together. Layer norm equals to gamma x minus, okay, multi-head attention such that concatenation of head 1, head where head I equals to softmax of Curie I Ki transpose. Okay. The provided softmax helper is available for use. All weight matrices and are passed as arguments to each functions. All right, so I have to write all of the separate modular functions. All right. And here we have a good way to visualize it. You have the input vector. It goes into like the multi-head attention, within which generates, I guess which generates the attention scores, and then you create the, let's say, yeah, the final output is the attention scores and an mapping out matrix. And then you add a norm it, feed forward, add a norm it, and do it n times. All right. All right. Let's dive into the theory, right? Because we can take this time to learn a little bit more about the encoder block. Yeah, let me read. The encoder block is the fundamental repeating unit of the transformer encoder. Each block contains 2 sublayers, multi-head self-attention, and a position-wise feed-forward network, each wrapped with a residual connection and followed by layer normalization. Stacking n identical blocks produces the full encoder. Introduced in attention is all you need, the encoder block replaces recurrence entirely with attention-based token mixing and per-position feed-forward computation. The design remains the backbone of BERT, VIT, and many encoder-based architectures. What it is? An encoder block is one complete repeating unit of the transformer encoder. It takes a sequence of vectors, x, which belongs into the real space of t times d model, where t is probably the number of tokens that are fed into, number of tokens that are fed into, and the embedding dimension of the model, and produces an output of the same shape. The block does not change the sequence length or the hidden dimension. It refines the representation in place. Okay. Internally, the block has exactly two sublayers arranged in a fixed order. Sublayer 1 is multi-head self-attention. Every token attends to every other token in the sequence. This is the token mixing step. Because this is self-attention, the queries, keys, and values all come from the same input. Okay. And then the sublayer 2 is position-wise feed-forward network. A two-layer perceptron, two-layer multi-layer perceptron applied independently to each position. This is the channel mixing step, where each token's representation is transformed without any interaction with other tokens. Each sublayer is wrapped with a residual connection and followed by a layer normalization. The output of one block becomes the input to the next. And the final block's output is the encoder's representation. Some of the key equations are the residual plus layer norm. Sublayer 1 self-attention with residual and layer norm is multi-head self-attention of means the query are all derived from the same input. The residual adds the original x to the attention output. And then layer norm is okay. Oh, yeah. I think earlier I said softmax, but yeah, the activation function is ReLU. Dimension of feed forward to sublayer output okay. Let's look deeper into the two sublayers. The two sublayers have a fundamentally different purpose, and understanding the division of labor is key to understanding the encoder block. Sublayer 1, multi-head self-attention token mixing. This sublayer allows every token to gather information from every other token. Given input x, it computes the query matrix, the key matrix, and the value matrix. And then the attention matrix is given to us by the softmax of the similarity scores scaled by the key dimension, the square root of key dimension, and then multiplied by the value matrix. Query key and value are projected from the same x. This is what makes it self-attention in the multi-head variant. Separate attention computations run in parallel on subspaces of dimensions dk equals to d model divided by h. Then outputs are concatenated and projected, which h equals to d. Each head uses dk equals to 64. Yep. And d model here would be what? I see, 512 something. Supplies a one that represents how much each token compares. Okay. So these these language seems to be very important. Where sublayer 1 does the token mixing, it tries to compute every kind of dependencies that each token has to every other token, and then generates like the final, I guess, like a transformed token matrix. And then it is given to the feedforward, where each vector is transformed by the same feedforward network plus layer normalization. Not layer normalization. Each vector that has already been transformed by the multi-head self-attention layer is treated with the same, I guess, like feedforward network, such that each, applied to each position separately, no information flows between positions. The feedforward network expands from D model to DFF, applies ReLU, and projects it back. Right? So it expands the space to a high dimensional space, and that does some operations there, and then maps the output back into the D model space. Usually the expansion is a multiple of 4. Complex per token transformations. Think of attention as which tokens should talk to each other, and feedforward as what to do with the information each token has gathered. All right, post-norm architecture. This is what I think I was remembering. The original paper uses what is now called the post-norm configuration. Layer norm is applied after the residual addition. This is distinct from the pre-norm used in GPT-2, Llama, and most modern architectures, where you have, let's say, original letters, layer norm, expressive, where you have output equals to a layer norm and then the subnorm. So you add the residual connections after residuals after the norm has been done. And in the pre-norm, you take the norm of it before you even put it into the sublayer. Residual connections. Each sublayer is wrapped with a residual skip connection. Instead of computing y equals to f of x, the block computes y equals to x plus f of x. Gradient high weights. During backpropagation, the gradient of y with respect to x becomes 1 plus partial derivative of f of x with respect to x. Oh, identity matrix, yeah. Why the specific order? The paper context. The encoder block was introduced in Attention and So On Unique paper. The paper's encoder configuration: 6 identical encoder layers stack sequentially. Okay, 512. All right, I think I have enough of the theory to start coding, and then I can come back if I run into any roadblocks. Right? So let me just copy the code and do what we usually do, which is create a notebook, new notebook and drive. What is the problem here? Dun, 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 dun. All right. All right, let me try to remember the formula of the layer norm. Right? Layer norm is something like x prime. Its layer norm is something like, where is it? Yeah. So generically speaking, you have the layer norm of x equals to gamma multiplied by x minus mu divided by the square root of sigma square plus epsilon and then plus beta. Right. So the thing is, this layer normalization should be independent of the column numbers, right? Like, so X can be an input matrix. So that means I'm trying to remember, like that means the mu and the sigma should be calculated across the row. And in this case, it would probably be in the axis, second last axis of last axis, actually. No, second last axis. Last axis is the column. So let me try to remember. So we want this. This will be a. Let me try to get some sample test data. All right. So let me try to assess what this looks like. Okay, so we still have a matrix. Okay, what does this look like then? X minus mu. Oh. So what do we want? We want 1 minus 1.5, which is negative 0.5, yeah. 2 minus 1.5, which is not negative 1.5. So it's currently subtracting 2 minus 3.5. So we need the shape to be different. Let's see. I think there was this keep dimensions equals to true. Yeah, and then print mu x minus mu equals to, it looks like what it should, which is 3 minus 3.5 equals to negative 0.5, 4 minus, okay. Da, da, da. All right, let me try to test this with All right. This is what it looks like. What does it look like here? Okay. I think that looks correct. So let's try to remember, what does multi-head attention do? Yeah, so first you decompose it into dimension of k equals to dimension of actually, no, I don't really need to do that as well. So what do we have? We have an initial set of query key and value matrix, but when we decompose them, when we project them into the smaller subspaces, you have actually WQs. Let me try to get some test data. Okay, if we have, for this, how many number of heads do we have? One. So that just becomes let me try to remember. I think it was something like a normal attention head would take in the X matrix and then generate the Q matrix using the transformation of X, W, Q. And let's say the X is what? Token number into dimension of model. So this would have to be the dimension of model times dimension of Q or K, right? Similarly with K, similarly with value. And then what you would do, you would use these two to calculate the similarity score scaled by the square root of dk, which would just be what? Curie, the similarity score of qk divided by dk. Then you combine these two and get the attention scores as the softmax over the similarity score scaled by dk multiplied by the value matrix. But if we have a multi-head attention, what happens? my initial understanding was something very similar, right? Like that it would create their own kind of query matrix, key matrix, and value matrix, and give us their own attention score, and the number of heads is given by d model divided by dk. Is that, if I remember correctly? Let's see. dk equals to d model divided by number of heads. So d number of heads equals to d model divided by dk, which sounds right. But let's see. Attention score. Yeah, let's see if it's head 1 equals to query prime 1, q2 attention about attention 1, but this would have all the x values. This would probably be confusing. Goes to what? And then once you have like a prime 2, a prime number of heads, then the actual output here would be the concatenation of these matrices multiplied by W out. So at this point, the dimension would be what? Token times d of k. And W out would have to be like dk into d of model. Let's see. All right. Let's see. Let me try to remember. Go back. Attention. So see, that is interesting. So does this mean so this means that they already have to calculate Q. That's okay. Let's see. Let's look at all right. Let me clicking here. You can just first do the projecting to the subspace, which is Q prime goes to Q, where Q would have the dimensions of and here I don't understand if this is the same. So you apply the Curie matrix and the key matrix again to the weights of the Curie matrix again to the Curie. That is, so wouldn't this be just like the subspace would just be like weight squared, weight of Curie squared. Let's see. So initially it was to generate the Curie matrix, you would have to do X times WQ. And then to generate the Curie prime matrices, you would have to do what? Curie times WQ, right? Such that Curie I becomes like, you can just separate it like that. But that implies that it is just what? That the big Curie prime matrix is just WQ, XWQ squared. Is that the right way to think about this? Let me just ask. Okay, so I guess my worries were misplaced. Yeah, no, WQ is not the same weight matrix used to generate a previous Q matrix. It is a single matrix that transforms your X into the total Curie space. Here's the direct breakdown on how the linear projections and head splitting actually works in multi-head attention. One-step projections, you do not calculate a Q and then multiply it by WQ again. You multiply by the input sequence directly to get the Q matrix, no squared. Okay, but that's interesting. Okay, let's try to. The model projects X into a Curie matrix. The reshapes the finite to the logical split. The software rearranges. Oh, wow, that's not that good. You know what could be helpful? Okay, let's see. Okay, so here it's saying something different, which is suppose you have the input matrix and then you use the WQ to make the Curie matrices, and then Curie prime is like just a reshaped matrix. Okay. But this is strange though. Yeah, dimension the big K. Mm. I feel like I need to study this a little bit more, because here you have this, but in the code it's something different. Let me just go through this grind. Okay. Dun, mm, mm, Da-da-da. I don't know if it's axis 2 though. Axis probably, if it is anything, it's axis 1. All right, then let's compute. You'd have what? Dun, dun, dun. Let's see if this works. Then I don't think I need to do this. Think let's try a test, shall we? Actually, an easier test might be just adding this here. Let's see. Oh. Yeah, you first find the shape. That makes sense. List cannot be interpreted as an integer. Where is the integer coming from? You know what? Actually, let me just move this. Right. Yeah, we're back. Dun, 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 dun. So where is it happening? Yeah, it's happening here. Attention of q primes I, k primes I, v primes I. Yeah, you can't do that. I'll have to do this. Possible images. Oh. Is it a list? It's a list of fucking arrays, yeah. My bad. Okay, so now where are we at? We are at s equals to np dot transpose. Oh, I thought. Ah. Okay, so we do have something. Let me just do this. And does this look? To the 4. This doesn't look correct. I see. So you have two attention. That's why. But they're not being concatenated. This should be a list, and the length of this should be 2. Actually, maybe I don't understand how. If it's 0, what happens? 4 to 2, but that's not what we want. We want 2 to 4 is also not. Is it? Oh, submissions. Let's see how I did it. So it must mean that I am doing something wrong with the 0 minus 1 minus 2. Does that look right? Yeah. And at v hat. This looks right though. Oh, so this attention is wrong. It's producing two 4x4 attention matrices, which is seemingly the source of our problems. And let's see, where is it coming from? Is it coming from? Okay, IK prime is primes for I in range. Splitting the number of heads is done by that. That's right. Number of heads. That looks to be the problem. So currently, how many? But then there's no need for this then. Which I guess is the right answer. Did feel quite redundant. Let's see, number of heads. In this case, it'll be 2. So but I still get 2, 2, 2, 2, 2, 2, 2, 2, 4. 2 to 2 for what? A single attention. Wait a minute. Let's just check. Huh. Okay, that's interesting. So it's just barking up the wrong tree then. I thought the output had to be the same shape as the input, but I guess not. Oh, but I guess it is, yeah. Let's see. Yeah, 2 to 4, where 2 is the number of tokens. And we have bashed it. That's the interesting thing. Okay. Feed forward. No, not this. This should be a good implementation. Getting it right now. I yeah. It's like that is incredibly stupid of me. All right, let's see. Yeah. That is incredibly stupid of me. But it is what it is. I think it's this. If I am remembering correctly, you don't ReLU the last output. All right, so let's see the encoder block. You have the inputs of the data matrix, or like the data, which the shape of which would be the batch size, number of tokens per batch, and then the embedding dimension or the dimension of the model. And then you have, you plug it into the multi-head attention to get MHA to be what? Multi-head attention of Q. Okay. That is interesting. So let's see. Let's try to remember where to plug the residuals in. So you plug it into the first multi-head attention, and you get what? Curie key. So okay, if this is the case, I mean, it looks like the explanation of this in TensorTonic, at least that's how it is being done, right? Like, so you apply the weight matrix twice, so to say, because to generate the Q prime, I have to like apply the WQ transformation again inside the multi-head attention layer. All right, but that's okay. Once I have this, I can just pass that into sublayer 1. Okay. Let me try to remember. It's add plus norm. All right, a residuous. Okay. Let's see. Yep. right, let's see. Oh, stupid of me. Oh, I didn't realize there was 2 gammas. But probably, yeah, I guess that makes sense. All right. Let's see if all the tests pass. Some tests are failing. All right, so probably have to ask. But that's interesting. But then where is it getting the Q from them? Doesn't mean that. So doing this, I should just do this. Which I guess makes sense because it was written as so here. Right? It's like attention of XXX. But that's interesting. Why did it pass the earlier time? What is the next module? Let's see. All right. I think I'll call it here today. I know we said like, well, I know I said I might go through this today, but I'll leave that for the next stream as part of to just like round the attention is all you need. I thought to like fully do this and then maybe like read a little bit of this, like the attention blog post, and then maybe implement a small transformer-like model. But then I have to see, or I might just move on to like some of the other research problem sets here. But I do think I need to like sit down, so to say, metaphorically, and then like fully digest the information that I learned and try to like implement everything on my own without much of the hand holding that these problem scaffolding does, albeit they are very helpful. But yeah, I mean, it like it took I took much longer than for this, like than I would have liked to, but I have had fun just like finishing this module and finishing going through this paper and like getting to know some of the more intricate details of the paper, because you kind of hear about this paper quite a lot if you are in like AI, or like if you are in CS, or I guess like these days it's you kind of hear it like every time, or like you kind of hear it like as long as you're somewhat close to the periphery of AI. And it's good to like just go through this and like crunch on it a little bit. So what would be probably interesting is like we did with the encoder block, I might just try to implement like a decoder block to see like how what to say different it is. I mean, the standard architecture is given here, or I could just look at here. Let's see. Where is it? So yeah. So let's think about it. All right. So this is the encoder block. Before that, you have the inputs, and then they get like tokenized, which is probably in this arrow, and then it goes to the input embedding. It gets transformed into embedding by like an embedding matrix, or like an embedding weight, or like an embedding transformations. It gets injected by a positional encoding, which in the paper is the positional encoding use is like a sinusoidal injection, where like the two subsequent tokens positions are always like, I guess, somewhat linked, and then it gets passed into the encoder block, which, as we have seen, the input gets split apart into and given to like different n heads, where the number of heads is equal to like the dimension of the model divided by the dimension of the key slash weight slash dimension of the key matrices or query matrices or value matrices. And then once the attention scores have been calculated, they get concatenated and they get like output transformed back into the dimension of the model by W out matrix, and then they get like add and norm. Add here is just like adding the residuals of X here. The norm is Lie normalization, which tries to control the transform representation before it explodes, right? Like, and then it gets passed onto like a feed forward network, which expands into like a in the paper it's said to be like 4 times the dimension of the model. So for example, if the dimension of the model used was like 512, it would be like around 2000. And then there would be some operations, like some nonlinear transformations, and then like they get transformed back into the space of the model, the embedding dimension model. And then you have like an add and norm, and then you do it like n times over, depending on like how much you want. And this stage of the encoder block is what is called as the token mixing, where you kind of learn where the representation that is learned is basically influenced by like trying to figure out the dependencies of every token with respect to every other token, right? And then this is the channel mixing, where once you have like the mixed representation, each channel or like each represented vector at that particular point gets treated the same way and gets projected upwards into the higher dimension space, and like maybe some computation is done to extract some useful information that again like compress back into the smaller dimensional space, which in this case is like the dimensional model. And that's just the encoder block, right? So if you just like split apart the encoder block, you get something like the embedding model, where you learn useful embeddings for a given input. But if you connect it with the decoder block, right? Like, so let's try to. I mean, I don't think we have touched much of the decoder block, but like each of the individual things should be understandable. So let's see. Once like a fully transformed, encoded signal, or like a data, or like vectors or matrix escapes from the encoder block, if it does enter, it can enter through a multi-head attention matrix, so a multi-head attention layer, and then it gets where you get added by an output embedding. Okay, so it is not as simple as I would have liked. But let's try to approach it from here, right? So if it's just output, let's say I give it like an A, and then it gets the output embedding, and then it goes to the same kind of process, mask, multi-head attention, where the process of masking, I don't think we touched much on the masking part, like, and I do think like we'll probably learn about it more in the BERT paper, where you essentially mask the attention scores of the future tokens that the model should not see, at least at training, and then you add a norm it, and you go through the multi-head attention again, feed forward again, you do a linear layer, softmax, and then sample from the distributions and add back into the output, and then regressively generate. Yeah, I think so. That's like a bit. This is a summary for myself. But as I said, I think there's a lot to be scratched here, and I know the architecture has gone through like so many changes and so many, like, I guess, improvements. So I would love to go through this and like implement code by code. And yeah, I'll probably do that next stream, or maybe the stream after that. I do think I want to get in a learning session for PyTorch, because there was a time when I learned PyTorch, but I haven't like used it in so long that I'm basically functionally illiterate in it. I can probably read it, but I cannot write it. That's as with like many other things. Same with NumPy. But yeah, that's kind of the plan right now. Hope. I'm liking this, you know. It is a very this is not the first time I'm saying this, but it is a very strange experience, you know, of like just working on something that I want to work with, want to work on, whether it be like studying, learning things, but like doing it for the camera, streaming it for n equals to 0 amount of people. But it's genuinely been a very fun experience, actually, and I hope to continue doing it. I don't do this for like people to notice it. I just like the experience for now, and I think it creates accountability on my part, and I think it leaves a trace of evidence of like just me, a caveman, trying to understand things, right? I think that's a good thing, especially in this era. Okay, hope it has been fun. I'll leave the stream here, and I'll end it. All right.